So hello and welcome to the Research Connection Speaker Series. This series highlights the relationships being built across our teams and the exciting work that is happening in the industries Autodesk serves. If you are in research and have an external speaker that you think is interesting, invite them to participate as a speaker in this program. I'll share a link in the chat. I'm excited to introduce today's speaker. Arvind is a master's graduate of industrial and product design from the Rhode Island School of Design, RISD for short. I had the opportunity to meet them a year ago during a portfolio review and think some of their work, especially around mycelium, is very interesting and applicable to some things that we're seeing here at Autodesk. So I'm excited to welcome up Arvind. So we're going to
Thank you so much. Thanks for the intro. And hi, everyone. I'm Arvind. And I'm going to talk about my master's thesis, which was to design regenerative materials for prototyping using local waste streams and mycelium, which is the vegetative part or the underlying under the soil structure of fungi or mushrooms. And I'm going to split this presentation into three parts. First is about materials, matter in general. The second is about mycelium, the experiments, our process, some of the findings. And the third is about the system model or a microsystem that could be applied for this. And before I start, I want to talk very briefly about where I'm from. So this is a picture from my home in India, and I got to grow up beside a national park, which was really interesting. It was an educational campus beside a national park, so I spent a lot of time doing hiking, photography, and that's where my interest in nature stems from. And coming to RISD, one of our first courses in our program was a shop orientation where we explored different materials, one of which was foam or EPS. And as a cohort, one of the things we noticed was that these materials are unsustainable, but they're also, when you work with them, they have so many particulate matter that is released, which is harmful to humans, our health, as well as the environment. So, looking at this kind of problem of prototyping with plastics, I was interested in seeing how we can sort of like going deeper into that, seeing how we understand where these materials end up. And I visited the Rhode Island landfill, which gets more than 90% of the state's waste, and they recycle around 300 tons of wood fibers, paper, plastic, glass, metal. But the thing is, most of these materials, even though they are recyclable, they still end up going to the landfill and being sealed in a plastic cover. And this landfill is expected to close by 2050 because 4 out of 6 phases of its area are already full and it's filling up fast. So we know that materials have been trying to be recyclable, but many times, even after a few rounds of recycling, a few cycles of recycling, they do end up being unusable or they have lower performance, so they end up being waste. And my question was, how might we design a material microsystem for students, makers, that can improve this sort of material utilization or resource utilization, as well as minimize the environment associated with it. Um, and there are various frameworks available to look at ecology and environments. And this is one this is called the donut economic model, where we have a ecological ceiling, which has 6 or 8. There are various planetary tipping points or boundaries, like global warming, ocean acidification. And recent research showed that more than 60-70% of these planetary tipping points have already been crossed, which means that the climate change due to these things is just going to get escalated. So there's a very fine balance between what humans and we need, and what the planet can provide. So for me, it was about how do we make connections between these different fundamental domains of, I'm considering ecology, socio-cultural, and economy. And for me, talking to various people, scientists, professors, engineers, I realized that three values that were sort of resonating were resilience, efficiency, and access. Resilience is about being flexible in the time of in times of change, flexible in terms of whether it's 10 years or 100 years. Economy and ecology are connected through efficiency, I feel, because things need to be more optimized, so the cost can be lower, where people can actually feel like they can use these materials in a accessible way. And that brings you to access, which is not just the access to the physical materials, but also to the information, the knowledge that is required to use these materials. And by looking for materials that I can use for prototyping, I was working at the Rhode Nature Lab where I got to work with algae, fungi, different types of biomaterials. And fungi was one that really caught my eye, they piqued my curiosity because they have evolved for millions of years, being able to decompose organic matter, biological matter, or waste into elements which is usually nitrogen or phosphorus, and which those can be used by other organisms for new life. So mycelium is really interesting because it uses waste. It also captures carbon in its growth process, um, and it's efficient at doing so. So there's a traditional process of working with mycelium, of mycelium molding, and this I've split this into six parts from sourcing the waste, and we looked at waste streams that are local, that included sawdust and wood chips from local maker spaces, as well as some food waste streams like coffee grounds from local cafes. These materials need to be, these feedstocks or substrates need to be sterilized. The workspace needs to be prepared and also sterilized before we can set up the mold. And the mold can also be designed in different ways and produced in different ways. We tried cardboard, 3D printed molds, vacuum formed molds, and some of them can be reused, like the 3D printed ones and the vacuum formed ones. Um, these molds are then filled with the mycelium and the waste, which is mixed together and added with some water, which gives it the humidity to grow. And this growth process takes around 2 to 3 weeks before we dehydrate the materials. Where the water is released, it hardens, and we can use it as a more usable material. And finally, we can also do like things like post processing, where we are coating it with different finishes like wax or paint. Ideally bio-based coatings. Um, and this is one workshop that we did at SD where um, we had the traditional process where students learned how to do it. And we realized that there were a lot of problems in this process because, first of all, it takes really long. You need to have a lot of things set up. It's a bit expensive to bring all the equipment and ingredients. There's also a lot of contamination issues if it's not done carefully because the mycelium, it needs to have it just needs to have kind of the right conditions to grow, and it can get contaminated with other strains of mold. It can get contaminated with bacteria. So looking at these issues, and also seeing how students want to use mycelium to prototype, um, the idea was that we can have prefabricated bricks, which people can use without having to go through the entire process of growing materials. So we can grow these materials beforehand, provide them to students, and they can use them to use traditional tools and also new tools to work with them and make stuff out of them. So this was another workshop that we did where we provided these materials and students were able to try various processes. The ones that worked really well were things like band sawing, traditional glues and adhesives worked really well. One student actually broke apart the mycelium block and mixed it with clay to sculpt with, which was also really interesting. Um, Inserts and drilling works, but I think that it could be better because the material is slightly soft because of its composition, and it has the mycelium is generally not grown throughout the material. So the outer surface is usually harder than the inner, which is the inner part is usually a bit softer and crumbles a little bit more easily. So seeing there were still some limitations in these blocks. Um, so one of the processes that we tried, I got this idea from Andreas Mershon, who's leading the BioHab project at MIT, and he suggested that we should maybe try compressing these materials, and that worked really well. I got a heat hydraulic press, which is heated, and these plates go to about 200 to 30 degrees Fahrenheit. And using this in the last stage of the process, instead of dehydrating, we can compress them, and heating them and compressing them at the same time reduces one step and makes the process way faster, because otherwise in an oven it would take 12 hours to dehydrate. Here it takes around half an hour, 40 minutes to dehydrate, but it does use more energy. So finally, yeah, these materials performed better. They had higher strengths, higher densities. We were able to do machining processes more easily on them, including drilling and adding inserts. And the most exciting part for me was laser cutting on these materials because the traditional mycelium blocks, they would char, or they'd sometimes catch fire if you're laser cutting them, because like I said, there's wood sawdust, and wood chips inside them. This composition has more coffee grounds in it than wood, so it doesn't burn as easily, but it gives a really nice texture, and it's really great for laser cutting. So I have these two materials, the micro blocks and the micro sheets, and we want to compare these materials in terms of mechanical properties as well as experiential properties. So this mechanical test was done at the Brown Design Workshop, where we had 5 samples. For the micro sheets, the sample size, it had to be layered together to have the same sample size, which is about 20 by 20 by 40 millimeters. So on the right image, you can see that there's 3 layers of sheets that are glued together, and it's loaded vertically. So I would expect the actual strengths to be higher than what you see here. The red lines are the micro sheets. One of them, the adhesive came off, so it didn't work really well. The other one that you can see higher up is what one of the mycelium sheets strength came out at. That came out to around 1 megapascal, of compressive strength. Um, and yeah, the sheets had relatively lower strengths. I would expect the actual strength of the sheets to be 2 or 3 times higher than this, and that would be really interesting to have high performance materials like that. We also did density and water absorption tests by leaving these samples in water for 24 hours and seeing how much their weight changes. Density was measured just with a vernier caliper and a weighing scale. Um, and along with these mechanical properties, it was really important to characterize how people feel about these materials, the look and feel of it, the experiential attributes, the things about like affective, emotional attributes of it. So this toolkit, there are some samples here on the right side, so you can see these 2 samples there, which is the micro blocks and micro sheets. And we asked students to fill out the survey, and these are the results of that. And it was interesting to hear what people had to say about it. A lot of students mentioned that the micro sheets seemed more predictable to use. They seemed a bit more familiar, to like touch. They seemed a bit like wood and MDF, somewhere there. The micro blocks were a little bit more interesting because they were velvety, soft. So people thought they could use them for maybe new and different ways than the traditional materials. But both of them seemed like they were usable, and students were really interested. 60-70% of the participants requested getting these samples for their projects after this workshop was done. So from there, I think that mycelium prototyping materials, they do offer a lot of new ways to create with. They are versatile in the sense that we can we can change the properties of it by changing the composition, by changing the conditions of the process, and they are sustainable. By sustainable, I mean they are the carbon emissions of it are not as high, and it's actually capturing more carbon and it's emitting. I'll talk a little bit about that in the next slide. And I'm also mentioning biologically circular objects because, as I said, traditionally circular objects or circular economy considers recycling and remanufacturing, but I'm thinking about how do materials, maybe they don't need to last longer, maybe they need to be temporary and biodegradable. And that way, we don't need to think about industrially circular economy, but maybe a more biologically circular economy. This is the overall system map of all the processes that were tried. So starting from biomass growth, trying different mycelium sources. So we get fungi and we can get them in pre-grown kits, like companies like Ecovative that do that. We use Ecovative's mycelium for our experiments. We also tried using spores or spawn, which is in the initial stages of growth. So that's relatively slower, but has a lower footprint in the process. And also liquid cultures, which come in syringes, which can be also inserted into the waste. Molding processes, vacuum forming, 3D printing, cardboard. Cardboard molds are temporary. 3D printing allowed us to make more custom complex molds. Um, and in the mold design in 3D printing, actually, we were able to think about how do we create slits and holes for airflow, because having air during the growth phases is really important for it to grow faster, which was one of the metrics that we wanted to improve on. And from there, looking at inoculation, which is mixing the mycelium with the waste. And we used coffee and sawdust, both as waste streams. Um, Different conditions, usually around 60-70% of humidity, um, also around 60-70 degrees Fahrenheit of temperature. Um, partial light is ideal. It needs to have a little bit light so it knows the day-night cycle, and having enough airflow for it to grow. Once the material is extracted from the mold, there's different ways of dehydrating it. Initially, we used ovens and of course, I mentioned compression, but we realized that for the microblocks, we can also use solar dehydration, which is which would be relatively like a zero footprint process. We can just leave it out in the sun and it dehydrates on its own. And what we're thinking is we need to sort of use these processes, make it as streamlined as possible. The students can use it for prototyping, research, and also have access to a information library. So currently we're working on a website um, that's like a mycelium library, but not just for the formulations, but also that can tell people how to source materials, how do we create the process, what's the best process for a certain application. And I'll share that also in a while. And finally, yeah, it goes back to landfill and compost, which is of course contributing to the biologically circular system overall. And this slide shows the life cycle exploration. I'm calling it exploration because a life cycle assessment is usually really complex. There are so many parts of it that are involved, especially in terms of sourcing, and we're depending on systems and infrastructure that has the inertia of problems. So I'm considering only parts of the process that I have used. Um, and initially, we had a system where we are looking at maybe having transportation for mycelium and the waste, which is carried from the source of the waste to our lab, and considering using ovens and microwaves for dehydration and sterilization. But I realized that if we use solar, a lot of those processes can be avoided, especially dehydration and sterilization. So without those, we were able to show that mycelium is actually um, carbon capturing overall in the process that we used. And this was around 1,200 kilograms of carbon per year. This is considering 2,000 blocks of mycelium per year, which is what I think can be produced in one lab, one or two labs which have a mycelium tent to grow stuff in. And comparing it to EPS or traditional foams, we can see that it's so much better. It's a stark difference, um, which goes to around 2,900 kilograms of carbon emitted. Um, so this was sort of where I'm still like interested in. I'm trying to see how much can we push this, how much carbon can mycelium capture. Usually, we need to look at the microstructure of mycelium to be able to calculate how much carbon is captured in it. But we can also average out because we know that half of the sawdust or half of mycelium, 50% of its mass is carbon. So that's how we calculated how much carbon is being captured in it, like embodied carbon is being captured in it. So from here, I just want to like talk about a few areas that I'm interested in taking this forward. Like I said, microstructure analysis could help us understand the actual precise carbon content of these materials. It can also it can also help us understand how materials perform at a micro level, which can then be emulated maybe at a macro level. So controlling some conditions, controlling some of the molds or processes. One idea was that using colloidal solutions or solutions which have other particles mixed in, like maybe metals mixed in. Maybe we can see metal particles in the microstructure if we use those kinds of compositions. Another area was 3D bioprinting, which is really interesting because I have some background in 3D printing, and I was interested in seeing how mycelium materials can be 3D printed. And it's really tricky because it the extrusion part we figured out because by designing a nozzle, having a certain nozzle thickness and having certain forces, seeing how we can kind of extrude materials. But the mixture needs to be extremely homogeneous and consistent. The water and material ratio had to be like adjusted so we can get some sort of height. We were able to achieve heights of 20, 30 millimeters. And I think it could be way better just by optimizing it a little bit more. But one of the areas that's interesting is how do we sort of avoid contamination? Because once we 3D print stuff, it needs to be enclosed in a space which doesn't get affected by external contaminants. So maybe 3D printers for mycelium need to have certain features where they're enclosed, where we can maybe take a box from the printer, leave it outside to grow, and have another box that's inserted where a new material can grow. Um, so yeah, I'm working on this 3D printer right now, and finally, I'm also interested in Mycelium CAD because current software for Mycelium don't, or like for 3D, don't really consider biomaterials. Um, and because they have custom properties, they have custom values. So seeing how we can maybe have molds or 3D models that can help us simulate how mycelium will perform as a material, or help us simulate how fast mycelium will grow in a mold. So these are some of the areas that I think could be really interesting in the future. And I think that's the end of my presentation. Thank you so much. Um, I've kept enough time for questions, so I'd love to hear any comments or questions.
Thank you so much. For those who are joining us on Zoom, please feel free to raise your hand, put any questions you have in the chat or in Q&A. And for in-person audience, feel free to speak up or raise your hand as well. Scott.
It's a great presentation. You know, as I was watching it, I thought, wow, we're growing this organic material and then we're shaping it with tools like bandsaws. And I thought, oh, that's, you know, this is exactly what we want. And then I realized, why don't we just grow wood? And then I thought, does mycelium grow much faster than it would take to grow the same kind of volume as from a tree?
Yes, yes, absolutely. I think trees grow pretty slowly compared to mycelium. I think in terms of nature, mycelium is really fast. Even organisms like algae are really fast. They grow up to 10, 15 centimeters a day. In terms of trees, bamboo does grow fast, but mycelium is still faster. I don't know the exact numbers, so I don't want to say a value, um, but yeah, because we are looking at waste streams, which otherwise would be discarded. It's also the speed that's important, but it's also looking at how, yeah, wood is useful, and wood is also a great biomaterial. It's still a biomaterial because it's bio-based. But for me, mycelium was more interesting because of, yeah, it's faster, but it's also sometimes it's capturing the waste that otherwise would end up going to landfills and emitting harmful substances into the earth. So that's why I think, yeah, mycelium is a good alternative to wood. Um, Even though wood is not that bad, mycelium could be better.
Thanks.
Thank you, Scott. Other questions? James.
Yeah, you said you had some real success with the laser cutting it, and then the bandsaw example you used. Have you applied it to any other subtractive processes, or like a table saw or anything? Like,
I did talk to someone who used the CNC for mycelium, and it doesn't work really well because once you cross the first, there's an outer layer um, of. Let me see if I can find a picture of it. Let me just show you these samples over here actually, because I have that. So the outer layer of this is the mycelium that you can see on the surface. And this grows up to like 1 or 2 millimeters on the surface. That's what gives it the overall structure. Inside the material, there's only probably like 20, 30, maybe 50% of mycelium. So that's why it didn't really work for CNCing, because after it crosses the first layer, it doesn't. But when you compress them, so this is thin because it's like one layer. But let's say I'll show you one more sample. If we have 2 or 3 layers of mycelium that are compressed together, like a double layer, basically, this is way stronger. And I think something like this could be CNC. I haven't tried it, but it's really worth exploring, and I would.
yeah, that's awesome. And I guess, like, have you done? Because you showed one example where you actually glued pieces together and then compress it. Does the opportunity exist to maybe put, like, stagger these to have like offset what's in between them, and then kind of adding rigidity as you go through?
Yeah, in this one actually, I didn't use glue. These two are just placed on top of each other and just pressed together. So the heat just makes them merge. Um, yeah, but yeah, like for the compressive strength test, I didn't do that. I just used glue, and that test would have been a little bit more detailed. Yeah.
But the laser cutting went really well, burning through it.
Yeah, this
Blades, the sharp metal objects, whatever ones, everything.
the preciseness and all of that came out really well with the test. Yeah. One of the
Other questions? Feel free again, raise your hand, put them in the chat. Adam.
For the carbon capture, in the graph you were showing, is that with using solar or is that using?
Yeah, the dehydration.
Repeat your answer.
Oh, sorry. Yeah, so this is using solar. So yeah, for actually 1 second. Yeah, this is using solar for sterilization. For dehydration, I've still considered how much emissions the oven or the microwave would take. Yeah.
Right. Okay. That makes
Yeah.
Yeah. You can see both transportation and dehydration having a decent impact. So it looks like that's cool.
Right. Thank you.
Do you know what the weight or the ratio of like mycelium to waste weight per sample is?
That's a great question. So I've used 40% mycelium and 60% waste, which is a higher concentration of mycelium than ideally. Ideally, we would use spores. The reason I used more mycelium, and this is ecovative mycelium, is because to speed up my process. This thesis had to be done as quickly as possible. So yeah, otherwise I would use spores, which would increase the timeline to maybe 3 weeks instead of 1 week, maybe even 4 weeks. But that would have a significantly lower, because currently, yeah, it's being we're buying it from equator, which comes from New York and it's being transported by road.
Yeah.
How sensitive is the growing process to temperature and moisture control?
It's quite sensitive. It's really sensitive to both moisture and temperature. It requires enough. If it doesn't get enough moisture, it won't grow as fast. And also it needs higher concentrations of moisture if it wants to grow outside of the material. So I've stopped the growth once the surface is covered. But if I let it grow for 2 or 3 weeks more, the mushrooms would sprout from this, which are edible. So that could be an additional stream of revenue or something that the food can provide. In terms of temperature, also it prefers slightly warmer temperatures. So we would freeze it if we don't want it. So when I get mycelium, which I don't want to use, I would freeze it and then it stops growing. 60, 70 to 75 degrees actually would be the optimal temperature where it's able to grow. Yeah.
Other questions from this crowd or online? No. All right. Well, thank you so much, everyone. Thank you, Arvind, for joining us today. And we will be sure to share out this recording once it's ready. Thank you all.